Okay. And now you should be seeing my screen, right?
I do.
Great. So I'll start by thanking Fabrizio for organizing this. It's actually really a pleasure for me to be able to share this work with my colleagues. And this is not actually a research work as it is a discussion among statisticians. You know, you'll see why I'm saying this because it would be everything will be based on very simple and almost off-the-shelf methods. So there is actually very little innovation here. We were just trying to be helpful and understand what was going on. So I'll be doing 4 things. The first is recap a bit about the epidemic.
Alessio, but we don't see the slides.
Oh, you don't?
We do. I do.
I do.
I do.
Oh, you do?
Now you should be.
No, I see the slide.
I do. That's okay.
You should be seeing my entire screen.
Yes, we do.
That's what we see.
Sì, le vediamo.
Yes.
Okay. Fabrizio, I shared my slides in the chat. Maybe you can. So if you don't see them, maybe you can download them.
Very strange. Okay.
Then I'm on slide 2. So my plan is to recap about the epidemiology of SARS-CoV-2, some things that everybody should know by now, but I'll try to say them, all of them. Then I'll be mostly complaining about public data. And then I will show 2 contributions, which is one is a short-term forecasting of intensive unit occupancy, which is something useful for planning mostly, and the general forecasting of the trajectory of epidemic indicators to see where the epidemic is going during the development of the epidemic. So SARS-CoV-2 is the new virus. It's got an incubation period. It's been observed from 2 to 14 days, but actually it's 5, a minimum of 5 to 14 days, and in most cases it's actually 2 weeks. Then at day 0 you have symptoms, and you can communicate the disease to other people from 3 days, more or less, prior to the onset of symptoms, up to 10 days. And people are infected mostly for 2 weeks. So it's a story that lasts more or less for 1 month. 2 weeks incubation and 2 weeks for recovery. But actually, the virus can live inside the body for up to 4 months, and even for a longer period. People that are infected since 3 months are not at risk anymore. They're not contagious anymore, but they are positive to the swab. It's got a very important morbidity and mortality. 10% infected need hospital admission, 1% die, and these figures are more or less 10 times. There is a tenfold increase with respect to the risks associated to the common influenza, to the seasonal influenza. Everything usually it's very quick. So after symptoms onset, there is a median of 7 days for hospital admission, and a very large probability of being admitted on the same days of the onset. So the onset can be with acute and strong symptoms, and the median time to death is 11 days. For people not dying, there is a long length of stay in the hospital. Often there is chronic morbidity even after recovery. So it's not a piece of cheese. Severity is strongly modulated by age, by gender, and by genetics. And genetics is a focus of research, actually. It's been discovered associations with the blood group, but with the HLA variant, but still under investigation. It's actually very important for understanding what happens. R0, everyone knows what it is by now. So the winter R0 at the beginning, during the winter season of the epidemic was slightly below 3. So each infected was expected to generate 3 secondary infections. Probably not everyone knows about the dispersion parameter K, which is the inverse of the variability around this expected value, and it is actually very small for SARS-CoV-2. And this implies that not everyone will infect 3 other people. In most of the cases, infected will not communicate the infection, and a minority, 10% of the infected, lead to most of the secondary cases. And there have been super spreaders, so someone who was able to communicate the disease to hundreds of persons. And this implies that the disease moves in clusters, often big clusters, and this implies that we must be careful, because if we are unlucky, one infected can lead to 1,000 infected in a couple of weeks. And a particularly dangerous period is the prodromic phase. And so when the WHO said asymptomatics do not communicate the disease, well, they were referring to people that are infected since 3 months, not people that are about to develop symptoms. These are very contagious, given that they have a large viral load, and they feel well, so they go around and communicate the disease. Most of the contagions happened in-house. I was joking on the 18th of May, where we were allowed to see our relatives, that of course we were allowed to see our relatives. We already communicated the disease to all of them. Isolation has not happened at home, in dedicated facilities. It has happened at home. So actually we have seen families of contagious. Contagious in families has been almost sure. A lot of contagion has happened in healthcare facilities. Hospitals now are much better organized, but still RSAs are more at risk. So healthcare, nursing homes facilities are still at risk. And clearly it happens in closed spaces because it's more difficult to dilute the viral load. So in workplaces, religious events, restaurants, university classrooms, and in crowded events. So for instance, there is a strong hypothesis that Champions League match Atalanta-Valencia that occurred on the 19th of February is one of the triggers of the largest cluster, most important cluster that we have, which is the one of Bergamo, where the seroprevalence is expected to be about 50% now. So clearly, contagion can be, you can catch it in very different ways. There are tales that are scary, but that are actually very, very low risk. An iris contact is being hit by a sneeze, and that's very unlucky. But if the ill person is not wearing a mask, it can happen. Okay, and this is equivalent to 30 minutes talking at a distance of 2 meters. Okay, and these are 2 situations in which you can be sure that you got the virus. Staying close, even without talking, is risky. Clearly, the risk increases with the duration of contact, the viral load of the infected, and proximity. So, for instance, two students attending a 2-hour class at the same table in university are at high risk. And if one of the 2 is infected, the other is almost sure of getting the infection. Type of interaction is important. For instance, voice volume. In course, we had spread of contagion. In meat processing facilities, we had spread of contagion also because they are very noisy. So people scream to each other, and they work in close proximity. So that's more or less it about what I wanted to say for epidemiology. Protezione civile data is very low quality. Let me complain a bit about the public data. We've been trying to get individual data from the ISS since February, but this was not possible. So we have daily counts by region, actually 21 regions, so 19 regions plus Trento, Bolzano. We have positive tests, and the definition of protezione civile is very cumbersome to me. They call it new positives, difference of cumulative cases. In epidemiology, there is a formal definition, which is incident cases. So people that were healthy yesterday and are infected today. Those are incident cases. We have counts of hospital and also separated ICU, intensive care unit occupancy. We have recovered, which correspond to a second negative test, deaths and swabs. And also we have data about the number of tested cases. Okay, incident cases are very biased. They are attributed to the day results are received. So there is a huge delay between the occurrence of infection and the when the infected is counted. The swab can date back 1 to 10, even 2 weeks before, and infection can date back from 3 days to 4 months before. And actually, a fraction of daily new positives in Italy, and especially in Lombardia, that we are registering these days, are people that were infected in April or in May. And the most important thing about this bias is that incident cases are only a time-varying proportion of the number of currently infected, which this depends on testing and tracing strategies. Okay, and this actually will be the focus of Professor Peracchi lecture, so I'm not going into this more. Also recovered is biased. Some regions counted the recovered patients that were discharged from the hospital, even if they were still positive. They are counted on the day of the second negative test, and this can be a long time after they are actually recovered, because least priority to access to swabs was given to home isolated. So waiting for a second swab, they could be at home, not sick anymore, even for a month. Also, deaths are not very good. Several notifications are late, up to months. Some regions are counting now deaths that occurred in April and March, actually. Intra-hospital mortality could be slightly overestimated, only slightly. It's counted well, but of course the DRG system is an incentive to counting deaths as COVID-19 deaths. So there might be a slightly overestimation. This does not compensate the strong underestimation about extra-hospital mortality in nursing homes, and in the worst moments, mortality at home was strongly underestimated. And actually, we are counting now about 35,000 deaths, but there are at least 10,000, if not 20,000 more. Hospital occupancy. The only count that we deemed reliable was ICU occupancy. The reason is that the Società Italiana Terapie Intensive, so the Italian Society for Emergency Care, issued guidelines for admission and treatment of COVID-19 patients. Tests for ICU patients were top priority, so the delay between counts and diagnosis is not large. So from January to May, these counts are reliable. Now they're not reliable anymore because for some reason someone decided to remove from the ICU count patients that are still in the ICU but test negative. So they are admitted testing positive, they stay in the ICU, and if they become negative during the hospital stay, they are removed from the count even before being discharged. and this, in my opinion, is crazy. But this is what happening since the end of May, the beginning of June. Clearly, what I just said is not true for general hospital admission, because this is dependent on availability and pressure on the health system. So several patients first they were sent home, then they were admitted, then the pressure became too strong, so they were sent home again, and now they are admitted again. So there is a bias that is time varying as well, if the patient does not have an interstitial pneumonia. Okay, so if the symptoms do not warrant admission for sure. The modeling strategy is compartmental models, for instance, the susceptible infected recovered model, possibly not the deterministic one, but models that take into account the network structure of the population, the stochastic nature of the contacts. Those would be the way of modeling and producing forecasting based on this data. Okay, there are limits. Those are chaotic systems. They are based on differential equations. Bias and misspecification can lead to huge differences in the outcomes. And so in general, it is recommended to use the complete trajectory of at least 2 outbreaks. And clearly, we don't have 2 outbreaks for the Italian case. As a proof of concept, let me say I'm not giving citations for obvious reasons, but most modified CIR forecasts were completely wrong. They could not even fit the observed data. They could not even forecast the following day up to a reasonable bias. So actually, in my opinion, compartmental models failed when applied to the SARS-CoV-2 pandemic. So we preferred using a direct data modeling approach. As I was saying, we did 2 things. One is short-term predictions. We try to be useful. So really, we are not medical doctors. What can we do? We can give accurate predictions. And the idea was this. If you can predict demand, then you can plan and rationing the health resources. And this is useful both for planning, for dealing with the epidemic, but also for dealing with surgeries that have been delayed due to the epidemic. So several patients, for instance, oncologic patients, were sent home instead of having their planned surgery because people wanted to leave beds free in the ICU. Okay, and clearly, if we can do a good planning, we can schedule also surgeries that are not related to SARS-CoV-2. Okay, so we have I call YIT my outcome, which is ICU occupancy, time T in region I, because that's the only thing I have, and PI is the population size in the area. So my count will be a number between 0 and PI. And I want to give 5 days ahead predictions, but this should be very accurate. Our approach has been to use the most recent 2 weeks each day to compute 2 predictors, and then we have combined these predictors in order to decrease the mean square error, so to get more accurate predictions. The first predictor is a non-stationary integer autoregressive model, so really nothing new here. But we find that this model actually captures, in some sense, the data generating distribution. So the number of beds occupied at time t is the number of new entries, which has got a certain trend, and which I'm going to discuss, which we can assume it's a Poisson, plus the number of patients that are still in the ICU from the previous day. So for each patient, there should be a 1 here. For each patient in the ICU at day t-1, I flip a coin with probability alpha with I. If I get a 1, the patient still stays in the hospital. If I get a 0, the patient either dies or recovers and is sent home or to another to another word. The trend, due to Taylor's theorem, any trend can be well, with some assumptions, any trend can be approximated with a polynomial. We compare the stationary with the linear, quadratic, and cubic. So the full trend was this one on the log scale, clearly. And we used BIC to check and to choose each day for each area. The clear limit is that we are estimating 20 separate time series models for counts. We are ignoring dependence among areas. So we have a method that is that has got low bias because it can adapt very well to the time series in the area, but it's got high variance because we are wasting information about the fact that different areas have similar trends. In order to mix information, to pool information from different areas, we use a general linear mix model. This is also off the shelf. So in order to compare counts among areas, we use an offset so that clearly the counts depend on the resident population. And also we use, we translate time given that the epidemic hit different regions at different time points. Okay, and I'm not going into this T tilde, which is estimated according to certain criteria. For each area, we have an area-specific parameter, but these area-specific parameters arise from a multivariate normal centered in common parameters, and this is what actually we estimate, and then we get posterior estimates for the area-specific parameters. The sigma is not completely free, but I'm not going into details on how we choose an estimate sigma. So let me say that this estimate will have low variance because we are pooling information across areas. Clearly, the bias will be slightly larger. So we have two competitors. One is low variance, one is low bias. What can we do? Which one do we use? Well, let's use both. So let's just make my final prediction will be just a weighted average of the inner and the GLM prediction. For the first 15 days, we use 50%, so arithmetic mean. And then we have chosen using leave last out cross validation for t+1, and really we left the next 3 days when we wanted to estimate at a 3-day horizon and so on. So by leave last out, I mean that I set apart the today, of which I know the measurement. I predict to today without using it for estimation, and then I minimize the difference between the prediction and the observed value. And I can hope that the best weight is for tomorrow is not too different from the best weight for today. Okay, something that makes statisticians proud and is not very interesting for everyone else. We using the delta method and Jensen's inequality, we were able to use to have a closed form approximation for prediction for standard error of the predictions. So we didn't have to do resampling and computationally intense stuff. It worked. What you see in black are the predictions, in red are the actual counts, and clearly the predictions were made, I think that's the 3-day ahead, that's 3 days before. So for instance, on 2 of April, I said we are going to have 1,300 beds occupied in Lombardia, and the actual count was indeed 1,302, I think. So we were off by two beds. As you can see, the prediction intervals, 99% prediction intervals, are embarrassing for the first days, but then they became shorter and shorter. Okay, and this is because for the first 2 weeks we did not have enough data, and then we were able to improve the model in some sense. So actually, the model that I showed you is the model for the here onwards. This is for Lombardia. Further validation, we have made public predictions for 90 days for 20 regions. So that's about 1,800 predictions only in 3 occasions. So 3 days by region. So 3 out of 1,800 predictions, the confidence interval did not cover the observed account. So this has been extremely reliable, more than the 99% that we were aiming at, and this is due to the use of Jensen's inequality. The absolute error, the median absolute error was 4 bets. So out of these 1,800 predictions, we were off by 3 beds in left at 50% in more than 900 cases. So it's been pretty accurate. Clearly, it's accurate, but it's useless if you want to say something about a global trend. So if you want to make predictions at the 2-week or even a 1-month time horizon. For this, you have to use a completely different approach, which now I'm going to introduce. Let me focus momentarily on the monotonic counts. So cumulative incident cases, recovered and dead. So no ICU, only counts that can be equal to yesterday or larger than yesterday. Okay. The cubic trend, as I said, is good locally, for short time periods due to Taylor's theorem, but the general dynamics cannot be polynomial. I hope this is clear by now. There are several reasons why the general dynamics cannot be polynomial. The simplest one to think about is the fact that you must have an asymptote. So the number of infected cannot diverge. If you have a population of 40 million, the maximum number of infected can be 40 million. You can't have infinite. Okay, that's why logistic growth curves are more appropriate to model the general dynamics, and given that they have asymptotes, and actually they also have parameters that I'm going to introduce, which exactly measure what you're looking for. So what we used, we defined, this is sort of new. Yeah, this is new. It's not a great innovation, but it's new. A generalized linear model with an identity link and whose expected value for the count follow a Richards equation. Richards equation is nothing but a logistic growth curve. There is I think 1 million of possible specifications for growth curves. We use this. The reason is that this BI5 is a peak, which is something people were trying to estimate. This is an asymmetry parameter, and BI1 is the asymptote. So for instance, if the estimate for BI1 is 50,000, then you're saying that in the end you will have 50,000 deaths when everything is over. So this is estimating parameters that are of interest, and it fits well. I will show you. We are using a negative binomial given that there is a lot of unobserved heterogeneity, so over dispersion. The mean is lambda IT. I'm using a simple specification for the negative binomial, and this phi is an over dispersion parameter. Once again, something that makes statisticians proud. We have closed form expressions for both the gradient and the Hessian, so gradient descent is very quick. Clearly, this is a very nonlinear model, so we use a multi-star strategy, given that the initial solution can lead to a local optimum. Especially in March and April, where still we were in an exponential growth phase, and we wanted to estimate the peak, that is to say, where the first derivative stopped increasing. So when the phase was not exponential anymore. We have created a shiny app. Actually, I'm going to show it to you. It's at this web page. And so you can estimate Richards equations for Italy. This is updated every day, and also for all regions and all counts. So this is one example for the number of deceased in Veneto. The count of Veneto is slightly more reliable than the count of other regions, given that a massive testing strategy was adopted in Veneto, and this has actually been very wise in my opinion. And as you can see, Richard's equation fits well, and this is not a Cubic polynomial. Okay, it starts linearly, then you have an exponential growth, then it slows down, and then you have an asymptote. Okay, and the red curve is the Richards. You have confidence interval for the prediction, and the black dots are the observed. This is estimated by leaving out the last 15 measurements, and 15 out of these 15 measurements are predicted inside the confidence interval. So it fits well, and it sort of predicts well. Not as good as what I showed you before, but it gives you, let's say, the long-term, well, not long-term, but the general shape of the counts. Clearly, non-monotony indicators cannot be modeled through a monotone equation, so they will not follow Richards. By non-monotony indicators, I mean prevalent cases, ICU occupancy, hospital occupancy, and so on. Prevalent cases is the number of currently positive by Protezione Civile. I don't know why they didn't call them prevalent cases, which is what every epidemiologist in the world would call it. To do so, we used a distorted mirror. So we pick a point, which is the point of maximum. Sorry, there should be a 0 here, 0 and 0. A point of maximum, which can actually be the observed one if you have it observed. Then you have a Richards going up and a Richards going down. Clearly, we are using the absolute value here, which gives symmetry at the TI0. But this symmetry is not a real symmetry. That's why the mirror is distorted, given that we're using different parameters. Okay, and then we have this constraint. If you do the math, this constraint is needed to guarantee continuity at the maximum. Okay, this is an example for Lombardia, intensive care occupancy in Lombardia. So this is the Richards going up, and then actually here, one day before the actual maximum, we estimate the mirror placement, and then you have a Richards going down. Once again, it fits, which is actually everything we are looking for when we try to model the general dynamics. I left out the last 15 measurements, and 14 out of 15 are inside the confidence interval. So it sort of also predicts rather well. As I was saying, also the parameters are of interest, and especially so clearly it's simple now, but we used this method here on the 15th of March. Already we had sort of what I showed you, and as you can see here, to say that it is going to slow down and then beginning a descent, it's actually not real scientific forecasting. So we want to estimate the peak, and this, let me share with you, has been one of the most dramatic events for me in March. On March 11th, so 1 week ahead, we predicted that using the ICU counts and by modeling also the delay between incident cases, ICU occupancy, deaths, and so on. So we use the multivariate model in truth. But by using this sort of method, 1 week ahead, we predicted the peak of incident cases for Lombardia. And actually, we announced it on Facebook, and we were on the newspaper saying it. And let me show you. So this is the hub. I've been disconnected. Let me reload. Let's see if it works. Yeah, this is the app. You can, if you are curious, you can play with it. Okay, so let me show you new positives by region. So incident cases, as I said, it's new positives by region. Think about it. Come on. Okay. It takes some time because this is doing computation exactly where you ask them, given that data are updated every day. They are downloaded automatically. So this is the time series of new positives in Lombardia. This is 21st of March. So on the morning of March 21st, we were in the newspaper, and in the evening at 6 p.m., 3,200 new cases were announced. So as you can see, we were a bit worried. There goes my credibility. But actually, this was actually the observed peak, given that later we did not have any larger number of new positives. And you can see here, this is the onset of the effect of the lockdown. This is before lockdown. So actually, the peak in Lombardia for new cases occurred before the lockdown effects. Let me go back to the slides. This is sort of another validation. Two slides about conclusions. One is further work. So these models were prepared with a 5-year-old going around. They were needed to be applied for the next day and not for the next few weeks. So they are almost off the shelf. As I said, this is not what I usually do. I'm a statistician, and my primary work is devising new methods and using new methods to answer new questions that could not be answered with available methods. These are almost off the shelf, really, for time pressure mostly. There are several limitations. This could be, in most cases, easily overcome. Also, several extensions that could be useful. For instance, covariates, and actually, we already have a code for Richard's GLM with covariates. I'm not completely sure we want to do that, though. One reason is that actually these simple models seem to work well enough. So, I don't feel too much pressure for improvement yet. And the other reason is that, really the world now is working on the pandemics. We got our understanding, and maybe I'm not sure that's the best route. Is looking for the precise model and whatever. I say this also because clearly for the Richard's GLM, we are completely ignoring the fact that we have time series, which I think should have horrified most of my statistician colleagues. And actually, let me say this, if you look at residuals, they are autocorrelated. And it's sort of the fact that we have an approximation guarantees to the standard error, and this is compensating for the fact that we are ignoring dependence, sort of. Some conclusions in general. What I can tell you is the number of epidemiologists that have been surprised by the occurrence of a pandemic. It is 0. Warnings about pandemic risks have been in the scientific literature since the 1990s, and we have also had 2 or 3 famous cases. For instance, H1N1, SARS-CoV-1, which is very similar to SARS-CoV-2, and pandemics end. This is not the first pandemic. It will not be the last pandemic, and pandemics end. I'm not going to tell you precisely when it will end, but it will end. The frequency of, to put a little perspective, the frequency of epidemics has increased also due to global warming. For instance, there has been an exceptionally dry summer and autumn in Southeast Asia, and dry seasons are linked to an increased risk of a species jump by viruses. Warnings about global warming date back much earlier than 1990s, and I think this is the top priority of our times, because it will not end. Epidemics do end, while the consequence of climate change are permanent. Okay, and I think that's about it. Thank you very much for listening.
Thanks, Alessio. Are there questions? Franco. There is a question by Franco.
Franco, you're muted.
You're right. Sorry. You're right. I understand your concern with covariates, but my looking at the data suggests that day of week effect might be present. So that is an easy covariate to include, I would say. Did you try? You think it might help? What's your view?
Yeah, it does. It does. Actually, we tried it. There is a strong seasonality, especially for diagnosis. The number of new positives, incident cases on Monday is always very low, given that swabs are not processed on Sunday. So every Monday we have newspapers saying epidemics is over, and every Wednesday or Thursday we have newspapers saying hey, epidemics is back. We have included covariates, so we included effects for lockdown, and yeah, the fit improves, and also the estimates make sense. I only would be very careful about causal claims, because in a non-linear trend, identification of causal effects is crazy. This we are not tried. So from a predictive and, let's say, association point of view, covariates are very useful. But if you want to make causal claims, then really it's a mess.
Yes, thank you, Alessio. I really enjoyed the presentation. My question is on data. Your complaint about data quality. I understand that there is a big issue on heterogeneity of quality across regions. And so that's something that I would like to know more a little bit on your sense of how this might affect the precision and the selectivity of predictions. Because if you have a sort of for regions that have worse quality data for some reason, then would we have automatically sort of worse predictions, and hence will be there further penalized for taking any policy actions? So they would be in a sort of catch-22 situation, or is it different, the mechanism?
So so as I said, for policy is there is a huge problem. So our models from a policy perspective are there as a proof of concept. So I showed you that with the counts I have, I can predict and I can explain the dynamics very well. But this is the dynamic that you communicated with me. If you give me the real counts, then I can use my model and tell you really what is happening. So actually, we are fitting the bias. So we have good predictions, but these good predictions are predictions to the observed data, not to the real counts, which we don't have. And actually, even for ICU, when the pressure was extremely strong, we had ICU occupancy, but this did not correspond to the demand, because several patients were moved from Lombardia to Puglia, from Lombardia to Germany, and they were not included in any count. So we have a spike in Puglia, which we are not able to predict. But this happens because they are not patients from Puglia. They are patients from Lombardia that were transferred there, and we have no way of getting that clear. So it's more a proof of concept. I can fit the observed data with them.
Alessio, if I can, I like very much the paper, it's very accurate. I think one issue which remains to be explained is regional heterogeneity, meaning that you explain very well the dynamic within any region, but the issue of regional heterogeneity, I believe it cannot be explained just by the story of super spreaders, which doesn't make sense. So I just tell you that we have two papers looking at the role of particulate matter and industrial structure. There's also another paper by Cuminelli showing, for example, distance from hospital or whatever. So I think it's very interesting to have a general idea of the issue to combine the two.
I think so too. I actually read your papers. They are very nice. They are looking at a feature of the epidemics which we have mostly overlooked. So the only relationships among regions that we are modeling is in the covariance of the random effects in that sigma that I showed you, which is time fixed. So that is there just to pool information. We have really no explanation about region heterogeneity, and that's an important question.
Alessio, I have another important question, which is one of the big issue now is the fact that the lockdown has kind of finished and now there is a new interaction between people. Does your model can say anything about this?
Yeah, it does. It does. So if there is a second wave, which is a consequence of the release of measures and so on, we will observe it, given that our research structure, also a mirrored one, is very strong. So once it starts decreasing, it cannot increase anymore. So as soon as we see consistently measurements outside of the prediction intervals, we can say something is happening. And this is not happening at the moment, for luckily. And actually, also the effect of May 18th is seen. So this has not produced such strong comeback of the contagion. So,
but isn't this because you don't use any covariates, or does it have to do anything like this? The fact that
covariates are not needed for that. So if you fit well and then you start underfitting consistently for 3-5 days, then this implies that it started going up again.
Alessio, sorry, very other small rough question. If we just look at data, we see that every day we have around 800, 1,000 less actual people under contagion. And we are meant to think that in 1 month we are out. Do you think it's going to be more asymptotic and not like this? Yeah. And why?
Yeah, simply because the process of healing is asymmetric. So most people get negative in 2 weeks, but we have a very long tail of people getting negative in 4 months. Paulo Dybala took three months, and I wouldn't say that Paulo Dybala is an elder with fragile health. You know, that is why it will slow down until we get to 0. And actually, the official criterion is that we need to have zeros for 28 days to say that we are out of the epidemic.
Okay, no other questions? Then I pass the floor to Franco. Thanks, Alessio.
You mean the screen and not the floor? Let me see whether can I share the screen now? Let's see. Can you see it?
Yes.
Yes.
Yeah.
Okay,
perfectly.
That's good. That's good. Okay, this is joint work with Daniele Terlizzese, who is there. Daniele, are you there?
Yes, I'm here. Franco, can you put the screen, full view, because it looks very small.
It looks small. So let's see what I can do. Can you see it better now?
Yes.
Yeah.
Okay. All right. So what we try to do in this work is to come up with a quick way of estimating the prevalence of the infection in a given population. The reason we want to do this is that just looking at the fraction of people that are tested positive is not providing is providing a biased picture of what is going on because of the selectivity of the testing process. Namely, most of the people that are tested are people that are that have symptoms or are expected for a number of reasons to be at higher risk. So people that are asymptomatic are typically underrepresented. There is in several countries an ongoing, there are ongoing surveys. In some countries, they are just starting designing the surveys. In other countries, they are about to carry them out. In other countries, they are already carrying them out. But surveys, population surveys, are not without problems. And there are many problems. Number one, they are costly. Number two, they are rather complex enterprises. Number three, they are plagued with refusal to participate. Lots of people say, forget it, I'm not gonna be tested by someone I don't know. And they take time to complete. So what we wondered, what we tried to do in this paper is to see whether there is any useful information that can be put to good use in the data that are currently available. Of course, as Alessio was saying, the quality of the data is important. So I'm not going to discuss this right now, and I'll say something when I talk about the Italian data that we are using. So there are two concepts of prevalence that have a somewhat different meaning and different usefulness. One is the fraction of people that at a given point in time, let's say in a given day, are infected. And this is what we call point prevalence. In parentheses, we say infected and therefore infectious. But if I read, if I understood correctly what Alessio was saying, some people might be infected, but no longer infectious. And this is something that we probably have to take into account. Here we identify being infected with being infectious. And the second is the fraction of people that have been infected during a given period. So in particular, we look at a fraction of people who were ever infected since the beginning of the epidemic. They might no longer be, so here they might have, they have been infected at some point in time, they might have recovered, or they might still be infected. So is a different concept than point prevalence. There is a paper by Chuck Mansky and Francesca Molinari forthcoming in the Journal of Econometrics that focuses on period prevalence. Here we focus instead on point prevalence, and the reason is that we think that period prevalence is a somewhat complex concept and is not even clear exactly what the data that we have can say about period prevalence. So here is the kind of conceptual framework that we are using is one in which a person can be infected only once and is infectious as long as he or she is infected. And when the person recovers, she's no longer infectious. time is measured in days, and we assume that the population is a constant. So the key variables here are three binary indicators. One is an indicator that the person is infected on day T, we are especially interested in the probability that IT is equal to 1, namely that the person is infected on day T. Sorry for day T and T as a random variable. So T is capital T is an indicator for the person being tested the first time on day small t. And PT is another binary random variable that indicates whether a person received his or her first positive test result on that particular day, small t. We're going to make, for simplicity, an assumption that nobody is tested more than once. This is done for convenience. Some people are tested more than once, and actually those that recover or are declared as virus-free are tested twice, in fact. We are also making an assumption that Alessio discussed, namely that test results are immediately available. These assumptions are made for convenience and they are not realistic. They are made for convenience because they imply that if you test positive in day T, small t, it means that you have been first tested on, if you test positive for the first time on day T, it means that you have been tested for the first time on day small t. And if you were not tested on day small t, it means that you could not be receiving a positive test result for the first time on that day. Okay, these are just necessary implications. So the basic framework that we are going to use is one is from the law of total probability. So the probability here, I'm dropping the small t index for time. By the law of total probability, the probability of being infected is equal to the probability of being infected, conditional of being tested, times the probability of being tested, plus the probability of being infected, conditional of not being tested, times the probability of not being tested. Why is this useful? Because it tells you what's going on in practice, namely that you might observe the fraction of people that are tested and the fraction of people that are not tested. You might be able to observe or estimate the probability of being infected if you are tested, but you don't have direct observable information to recover the probability of being infected if you are not tested. Okay, so the strategy that we are going to follow is to try to estimate the probability of being infected by bringing in additional information on the probability of being infected given that you are tested and the probability of being infected given that you are not tested. Knowledge about the operational properties of viral tests is going to be helpful here. Now, by operational properties of viral tests, we mean the probability of type 1 error and type 2 error, respectively. So type 1 error is the probability of a false positive. So you are declared or reported as positive when in fact you are not. And type 2 error is the probability of a false negative. You are reported as negative when in fact you are infected. Of course, all this is conditional on being tested. Now, the way we read the literature is the following. The probability of type 1 error in the kind of nasopharyngeal tests that are used in practice, that probability is negligible. So we take it to be 0. On the other hand, the probability of type 2 error is non-negligible and is not due to the test itself, but is or maybe is mostly due to the way in which specimen collection is carried out. For example, the samples could be collected too early or too late. They might be contaminated, or they might sit in a refrigerator for too many weeks, 2 weeks, 3 weeks. So the viral load vanishes, but the specimen is 2 weeks old. At the time it was taken, the viral load was well present. The fact that it disappears 2 weeks later is just a problem with the way in which testing is organized. Now, the literature for beta, which is our probability of type 2 error, ranges from like 2% to a striking 40%, and the range that is often quoted is between 10 and 30%. Okay. Now, what can be shown is that under the assumption that testing positive means that you are tested on that day, and under the probability, under the 0 probability of type 1 error, you can write, you can show that the probability of being infected, conditional on being tested, is equal to the probability of testing positive, conditional on being tested, rescaled by 1 minus the probability of type 2 error. Okay? So this is an important relationship because what you do observe is not the probability of being infected given that you are tested, but is the probability of testing positive given that you are tested. So we have this from the data. And beta is something that we can make educated guesses about based on the medical knowledge. Now, these guesses take the form of a range, but this is okay. The knowledge of the extreme, the minimum and the maximum value of the range is informative and useful. Of course, if there is no probability of type 2 error, then you learn exactly from the probability of testing positive given for those that are tested, you learn exactly the probability of being infected. The two things coincide. So how about the untested, those that are not tested? Well, here we take the view that because of the way in which testing is carried out, it's plausible to think that the probability of being infected is lower among those that are untested compared to those that are tested. And this just reflects the bias of the testing process. They would be the same, those two probabilities, if tests were carried out at random, but they are not. In particular, if the testing is biased towards people with higher infection risk, that minus equally is really a strictly is a strict minus. So we define a parameter lambda, which is essentially a measure of the bias in the testing process, which is the ratio of the two probabilities of being infected. The probability of being infected among those that are not tested, and the probability of being infected between those that are tested. Okay, and we assume that lambda is between 0 and 1. I will say something more about lambda because there is some information that can reduce the range from the 0-1, which, if you want, is a very general statement, but perhaps not particularly useful. So I'll say something about how this range can be narrowed down. Okay. Now, if we put together the two results that you have seen, we end up with a relationship that is essentially our estimating equation. So the probability of being infected is equal to the probability of testing positive for those that are tested, corrected with two elements. One is the knowledge of the probability of type 2 error, and the other one is a measure of how far the unconditional probability of being tested is from lambda time. Sorry, no, it's not how far. It's just the probability of testing positive plus lambda times. Sorry, the probability of being tested, t equal 1, plus lambda times the probability of not being tested. Why is this relationship useful? Because there are quantities here that we can measure from the data, the probability of being tested and the probability of not being tested, the probability of testing positive given that you are tested. And then you have these two parameters, beta and lambda, that for which we can make some guesses. We can make statements about their values. And I already mentioned a range of values for beta, so let me turn now to a range of values for lambda, calibrating lambda. So here is a possible way of calibrating lambda. Suppose that in the population you have two types, those that are symptomatic, S equal 1, and those that are not, the asymptomatic. And assume that among the asymptomatic, the infection rates is lower, is positive, but lower than among the symptomatic. So we can define the ratio between the two probabilities. We call it mu, and this ratio we can assume that is greater or equal than 1. Then let's introduce 3 parameters: the fraction of the population that is tested, small n, the fraction of the population that is symptomatic, let's call it pi, and the fraction of the symptomatic among those that get a test, and this is small p. Okay, so among those that are sampled, testing and sampling here is the same thing. Small p tells what is the fraction that have symptoms. And as a measure of the bias in the testing protocol, take the ratio of small p to pi. Okay. If the sample is biased towards those with symptoms, that ratio, which we call gamma, is going to be greater than 1. Okay. How can we calibrate lambda? Well, we write down essentially a relationship that is another version of the law of total probability, this time applied to the probability of being infected given that you are tested. We are going to make an assumption here, which we think that is reasonable, that if you condition on symptoms, if you know whether someone is asymptomatic or not, the probability of being infected is the same whether you are tested or not. Okay, so knowledge of symptoms, being tested doesn't add extra information to observing whether you are symptomatic or not. So under this assumption, you can write down the probability of being infected among those that are tested. And you can also write down the probability of being infected among those that are not tested. So the lambda parameter, which is the ratio between those 2 probabilities, takes the form that you have here. So the expression here just decomposes lambda well, decomposing is not the right term, represents lambda as a function of the 4 objects that I just mentioned: mu, n, pi, and gamma. So let me remind of what these 4 things are. Okay, so mu, let me go back, is the ratio between the probability of being infected among the symptomatic and the probability of being infected among the asymptomatic. Gamma, you see here, is a bias, is a measure of the bias in the testing protocol, is the ratio between the fraction of the symptomatic that are tested and the fraction of the symptomatic in the population. Then n is just the fraction of the population that is sampled. And what else do we need? I think I discussed again. I mean, I reminded you of all the ingredients in this formula. Now, why we end up with this? We focus on this formula because some of the parameters in this formula can be calibrated. And we did a calibration exercise here using data coming from Italy and data coming from a specific municipality. You might remember the municipality of Vo near Padua. Is a small town where I think we had the first COVID-19 death in Italy. And that municipality was subject to almost complete testing between late February and early March. So we use this data to calibrate pi to 0.067 and mu to 17.9. Okay, and then for n, we take the testing rate in Italy, which is here is just a ratio, so is 0.6 out of 1,000. So it is less than 1 per 1,000. That's the testing rate on May 20 last month. So with these values here, with pi at 0.67 and mu at 17.9, you can produce a contour plot of lambda, okay? And you see that the darker color corresponds to 1, okay? And as the color fades, you get something towards 0, okay? And so the relationship for there is a trade-off between gamma and mu, which is essentially this hyperbolic thing. And as gamma and mu increase, you move away from lambda towards smaller and smaller values. The other, so for example, what you can do with these, how much time do I have? Long?
About 10 minutes.
10 minutes, okay. Okay. So here, what you could do is to read off values for lambda depending on range of values for gamma and mu. Essentially, that's the usefulness of this. For example, when gamma is equal to 0.15, which corresponds to the finding in VO, so the finding in VO is that fraction of symptomatic among the tested was 15 times higher than in the general population of VO. So with this value of gamma about 15, and you have that the values of lambda range. I'm just reading off the slide. The value of lambda range between the value of lambda.
Franco, can I interject you just a second? I think you are getting a little confused here. We don't observe in VO the gamma, because in gamma they tested the whole population, so we don't know what will be the bias in the sample. We're just saying that the range, the potential range of lambda in VO, given the other data that we observe, is between, say, 10% and 65%.
Okay.
So we read a vertical line on this contour plot, placed at 17, 18 essentially. So we observe mu, which is about 18, and then we go on the vertical line, and we see that then lambda varies between say 0.1 and 0.65.
Okay. But, well, okay, I'll take that. For some reason, okay, let's not waste time on this. Somehow I thought that there was something with the gamma equal 15 that is revealed by Vo. But anyway.
It is the maximum possible of gamma, because gamma cannot be larger than 1 over pi.
Yeah, okay. The other thing that we might want to discuss is the relationship between point prevalence and period prevalence. It is something that we have been trying to understand, and actually here is where perhaps some feedback would be useful. So the key question is, yes, we can recover point prevalence for the data. Exactly what data reveal about period prevalence is a little bit of an issue. So let's again think of a very simplified setting in which the population is constant and the infection lasts at most 2 periods. Think of them as weeks. Nobody dies. And so a fraction delta recovers in 1 week. The remaining 1 minus delta recovers in 2 weeks. So at each time, the number of currently infected is equal to the number of new infected at time in week T, and the fraction 1 minus delta of those that became infected the previous week. Now, in this setting, we define the point prevalence in the population as alpha t, the fraction of those currently infected out of n, which is the population size. And eta is the period prevalence, which is just the sum of those that became infected for the new infected each week from the beginning of the epidemic till the current week. So it's the sum of the I star from the beginning to now divided by the total population size big N. Okay. So you see that for the point prevalence, you only have essentially to figure out how many are currently infected. But for the period prevalence, you have to add up all those that became infected for the first time period after period, or week after period, week after week. The other thing that you can see is how many are those that recovered. Those that just recovered in the current week is a fraction delta of those that were infected the week before, and a fraction 1 minus delta of those that were infected 2 weeks before, because after 2 weeks, everybody is no longer infected. And you can cumulate up these infected, recovered people week after week, and that's what we call RT. Now, it turns out that the sum of the new infected from the beginning of the epidemic to the current week is just equal to the number of those that are currently infected plus the sum of those that recovered in all previous week up to now. Okay, so in the population, the relationship between point prevalence alpha and period prevalence eta is given here. So period prevalence, you can figure out what period prevalence is if you add to point prevalence the fraction, the cumulated sum of those that recover out of the total population n. Okay. Now the thing is, we have a relationship here that is valid at the population. What's going on in the sample? Because we typically do not observe what's going on with the recoveries. You don't observe what's going on with recoveries and with infections in the whole population. You only observe what's going on with infections and recoveries in the samples that you draw from the population. And possibly these samples are biased, as we discussed before. So let's consider the simplest case in which sampling is done at random and the virological test is perfect. So no type 1 and no type 2 error. You might say that this is unrealistic, but it gives some tractable results and is a useful benchmark. And furthermore, remember what I said at the beginning, that some countries are embarking actually in random sampling of their population. So here, what we show is that point prevalence can indeed be estimated from the available data. And the estimator is unbiased and is alpha hat t. The problem is with period prevalence. Period prevalence would require, if you have sample data, random sample of the population, learning about period prevalence would require you to be able to figure out not just who is infected today, but who was infected in previous times, in previous weeks. Now, virological tests are not gonna be able to tell you this. So what you need here is serological tests that are able to perfectly detect past infections. But unfortunately, the data that we have today do not contain this information. And we think that removing the assumption of random sampling that we do in this example is only going to make things worse. So we don't have a clear way, we think, of estimating period prevalence out of the data that are currently available. So the data that we have currently available are the ones that Alessio already mentioned. Total number of confirmed positive cases, number of new cases, which is essentially just the difference over time or between one day and the next in the total number of confirmed cases. Then the number of swabs, the number of tested cases, and then of course population comes from ISTAT. Is an estimate, the most recent is January 1st, 2019. There are a number of other data issues that some of which Alessio already discussed. So let me go briefly. Number of swabs overstates the number of people actually tested because some people are tested more than once. So the series of tested cases goes in the direction of removing most of those duplications. There is also a problem with a lack of alignment between the timing swabs were taken and when test results are released. And then for some regions, there are inaccuracy or errors in the data. The most important one for our purposes is one that affects the region of Lazio in April 24. So we consider data starting from April 25th. Estimation is to smooth out some of the observed, to smooth out the observed data, to remove, for example, seasonality. We take a 7-day moving average, and we think that these might also help with some of the data problems that the other data problems that I discussed in the previous slide. We take for beta a range of values between 0.01 and 0.5, and for lambda we take the full range. Of course, with these we have results that you might say are a range of values that are too wide. But as I said, the range can be narrowed if you trust some of the restrictions that I discussed earlier. So what we have here are estimated probability of being tested and estimated probability of being positive conditional on being tested. So the estimated probability of being tested is very small, but is particularly small in regions like Puglia, for example, where the epidemic was not as important. In other regions, those probabilities are higher. For example, Trentino Alto Adige is pretty high, Valle d'Aosta is pretty high compared to other regions. The probability of being positive conditional of being tested follows the usual pattern. Lombardy, that probability is quite high. The data here, I think they refer to May 20, so it's about a month ago. So the probability of being positives, conditional being tested, has gone down with respect to that month. But again, Liguria, Lombardia, and Piedmont tend to have the highest, and the southern regions have the lowest. Here is the full range of values for the probability of being infected. And you might say, oh, you go from 0 or something very close to 0 to 3.4, okay, for beta equal 50% and lambda equal 99%. Now, the point is that 3.4% is a very small fraction, even if it is the largest of all values in this table, logically largest. It's very far away from what herd behavior would require, which is, if I understand, something of the order of 60%. So even, of course, these are estimates of the probability of being infected today. Okay, so it's not accumulated value ever infected, but it's still a very, we think is still a very small value. Is a value that is small, but it varies a lot across regions. And here is shown. I think just quickly. The table shows the huge differences across regions for 3 configuration lambda and beta. And again, here is a graphical presentation. Umbria and the southern regions have the lowest values of the estimated probability of being infected. Lombardy, actually the industrial triangle, Piedmont, Liguria, and Lombardy, has the highest values of the probability of being infected. And then we show here how it changes over time and how it differentially changes over time across the various regions. So just to finish up, these are, let's say, quick and dirty estimates of the range of values that the probability of currently being infected can take, based on a set of assumptions that we think are reasonable and take for some key parameter, take the form of a range of possible values. Okay, I think I've taken a little more time than I wanted, but I think I'm done with my presentation.
Thanks, Franco. Any questions? Alessio.
Franco, I was a bit surprised to see that the probability of testing is not much larger in Veneto than in other regions. It's in the middle. I was curious if you think that is because maybe you are looking at late May, where in Veneto the epidemics was fading out. Maybe is that possible?
Yeah, it's possible. I haven't been comparing carefully the different regions and how they differentially behaved over time.
Let me add something, Franco, on this. We use for the testing the series of tested cases, not the series of swaps. And the series of tested.
Oh no, that's right. That's an important point. Yes.
So because that one removes all double duplications, so that's very important.
T is not the number of swabs; it's the number of individuals that have been tested for the first time in a given day.
Okay.
I see. Thanks.
Other questions?
I don't know. Maybe Daniele wants to say something. Possibly. I've been talking all the time, and and Daniele. I mean, I think that it might be worth having Daniele remarking perhaps on.
Well, no, I mean, I think you said almost. I mean, we did this together, so I don't have much to add. The only point, perhaps, on the very last point that you made, that observing the results, I would emphasize that even though the numbers seems small. I would rather emphasize that they are large rather than small, because I mean, true as you said, we want to compare with whether or not it reached herd immunity. I have a lot of background noise. Okay.
Yes, it's hard.
The point is that we're not measuring period, so we cannot say something about whether or not it is herd immunity. But we can say that if in some regions there are 2% or 3% effect, the risk that the infection will start again with the removal of social distancing and other restrictions is not. So perhaps the numbers will just caution in removing all the restrictions that down the infection so far. So that's the only comment I would add to what you said.
So I think that it's a little bit my comment also with the Alessio presentation. I think all these things are very interesting, but it's also related to what Daniele was saying. What's going to happen now with this removal of the lockdown? And that I think is the question that everybody. How useful are these estimates? Because they're done for a period when there was a strict lockdown, from what I understand. Mm-hmm. So can we say something about this, or can we put some covariates there that would capture the easing of the lockdown?
Well, Fabrizio, in fact, we can update those estimates to yesterday.
Yes.
It's
and
very
then
easy
what?
to do it, and then we see where we stand. My sense is that if we still have something around 1% of currently infected, that's risky. Then it's possible, as Alessio said, that some of those people that are currently infected are no longer infectious. That's a different story. That's a possibility. And if that is true, then we just be much more relaxed at it. But as long as the people that are infected are still infectious, 1% is not a trivial number. Once you remove all the restrictions on mobility and people start partying and being together and joining crowds and groups and so on, then infections can start all over. So in this sense, I think these data are useful. I mean, they are a sign of caution.
Well, I would add the following: that is definitely true that our calculations can be updated to today, and then what we could do is, like Alessio did, fit a polynomial of low order, like quadratic or cubic, in order to approximate local trends and see whether things go up or down or keep going down in the next days. It would be a local forecast that holds only locally for a few days after the current date. The question is, locally means what? 5 days, a week? I don't know, but this is something that could be done.
Let me add something else. I mean, we do not. If we observe the way, in which these estimates go, they're going down, as Franco showed in the graphs. But part of this going down is mechanical, or at least it's perhaps an overestimation of the going down, because we are keeping lambda constant. Now, lambda is a measure of the bias, and there are reasons to suspect that the bias is going down because there are fewer people that needs to be tested. There is no longer all the emergency in the hospital, in the ICU, and so on. So probably they are testing now people that are less and less with severe things. We don't know that, but they know. I mean, the health authority, particularly at the local level, I think they have a much better sense of how biased is their testing. So they could incorporate this additional information in the framework that and obtain numbers that are more informed. So I think that one part of exercise that we did is to provide handles where additional information that we as economists, as statisticians may not have, but the health authority might have, put together and to obtain more information.
Okay. Other questions? All right. I think thanks a lot for the speakers. It was a very, very interesting seminar. Both of them, they gave us a very good picture of what's going on. And maybe we'll continue this series of seminar on COVID next week.
Yeah, that's a great idea.
Okay. Yeah, I know that Leonardo has some. Go ahead. Thanks a lot to everybody. See you.
Okay. Thank you, Fabrizio.
Okay.
Thanks.
Bye-bye.
Thank you.
Have a good day, everyone.
Bye-bye. Bye.
Bye-bye.
Thank you. Bye.
Bye.
Thanks. Bye.
Bye bye, everybody. Thank you.